Welcome to qnawire.
All right. So for this problem, we have LRC parallel circuit. I'll plot the circuit over here. So this is the main branch, and there are three branches because they're in parallel. So this is the resistor, and this is the inductor, and this is the capacitor. They're basically in parallel. Okay. And the impedance expression. Let me see. Okay, yeah, the impedance expression for the parallel circuit is actually, I'll skip the details, but you can look up the previous question to find out the derivation of this impedance. So the impedance equal to 1 over R squared plus omega C minus 1 over omega L squared. Okay, so this is the impedance for the parallel circuit. And so for part A, we want to show that the resonance angular frequency is 1 over square root LC. So now if we look at this expression, we see that if the term inside this parenthesis is minimized, then the denominator is minimized as a whole, and then the whole term, the impedance will be maximized. So we just say omega C equal to 1 over omega L. So we can solve for the omega resonance or omega naught, which is equal to 1 over square root LC. And for part B, we have the resistor and we have this capacitor, inductor connected in parallel to the voltage source with amplitude of 240 volts. What is the resonant frequency, angular frequency? So we just need to plug in the numbers because we already have this L equal to 0.3 henries and the C equal to 0.1 microfarads. So just plug in the two numbers, we obtain the resonant frequency equal to 5,774 rad per second. So this is the resonant angular frequency. And for part C, what is the maximum current through the source at the resonant frequency? So the maximum current through the source. To do that, we need to plug in the numbers of the resistance, the reactance of the capacitor, and the reactance of the inductor into this expression to find out the impedance of the circuit, Z. And actually, we found that hold on, let me see. I think there is an easier way to do that. Right, because in this in the condition of resonance, we already have. I'll erase this. Erase it. Erase. Okay. Because in the condition of in resonance, we already have omega C equal to 1 over omega L. So by using this condition, we already have the impedance equal to R. Then we can find out the maximum current through the source, which is simply equal to V over R. Okay, so V is 240 and R is 100 ohms. So this is equal to 2.4 amperes. And for part D, so the maximum current in the resistor at resonance. And for part E, the maximum current in the inductor. For part F is the maximum current in the capacitor. So this we'll answer these three parts at the same time. So D, E, F. because this is a parallel circuit. So the potential difference at these 2 points. So suppose this is point A, this is point A, and this is point B. The potential difference at point A, for point A, B, they are the same. So basically, the potential difference between the resistor is the same as the potential on the 2 sides of the inductor and the capacitor. So in that case, we can find out the current in each branch separately. So like for the resistor branch, we have IR equal to V over R. All right, so which equal to which is simply equal to the one we found here, 2.4 amperes. And for the C, for the L branch, IL equal to V over the reactance of the inductor, which is omega L. And omega is the one we found here. L is given in the problem, which is 0.3 henries. So plugging the numbers, we found IL equal to hold on, let me use the calculator, see what it is. So V is 240. Okay. So it's 0.139 amperes. Okay. And for IC, the current in the C branch, it's V over 1 over omega C, because 1 over omega C is the reactance of the capacitor. So it actually have the same value as this one because it is in the resonance condition. So equal to 0.139 amperes. All right. So that's it.